I'm going to go through it again. I'm going to go through it again. Yeah. We just do it quickly. Yeah. Yeah. Go through it again. VCC. Yeah, we start recording just now, so that's why we need to go through it again. So in your homework question, you are given this network, and you are going to find out the current IC, and also based on this collected current, you are going to work out the value of R1 and R2, and this is the job that you need to do in this so-called DC biasing, and RC is given. So first, we establish the low line first. The low line VCC is equal to these two voltage, summation of these two voltage. Remember, right? Transistors are given two values, beta and the early event voltage. And we are going to use this low line, and then we work out the maximum current. And you have attended lectures. You should know that the maximum collected current is given by this amount, VCC divided by RC. This is the maximum current. This is maximum RC. So the operating point will be the half of the maximum collected current. So the base current will be the collected current divided by the value of beta. So now everything is downhill now. So what we need to do is to use this network, use this loop to work out the. Sorry, let me just finish here first. Now the next thing is we need to play with the Teflon and Norton conversion. So this one, the source voltage, this is VCC, right? If you don't mind, you can just rewrite this. So we have network like this here, yeah? And then one, and then VCC, yeah? We just the same voltage source, but we just draw it in a different manner. And the voltage here is going to be VCC. We should use the Teflon equivalence. The Teflon equivalent, or we consider these two combinations, the series combination of the voltage and the resistor. And you know, this one can be converted into the current source. The current source, and then VCC divided by R1, and then the resistor R1, and then our tone, and then so you can convert it into this manner. So in other words, right, you can just say R1 in parallel with R2. So the first conversion, after the first conversion, you went up with the current source here, VCC R1, and then the resistor is in parallel with each other. So after the first conversion, now the second conversion is to convert this. We have the current source in parallel with the resistor, and then we just convert it back to the cathode given. So if we do that, then this guy will become a voltage source, and then VCC R1, and then R1 in parallel with R2, and then R1, and then R2. So I hope this is clear enough, right? So now I'm going to copy this across. R1 in parallel with R2. And the voltage source here is VCC divided by R1 plus R2, right? If you just work it out carefully, right, you will know it is like this. So this is the eventual source that we are going to get. Now, the question is, uh, we need to find the value of R1 and R2. There are many ways you can do this, but before doing anything, make sure you understand that the voltage here is 0.7 volts. And with this in mind, and if IP is here, so this IP is here, then VCC R2 R1 plus R2 is equal to IP R1 R2 and then plus 0.7 volts. And with this equation, we have IB here, and then what we need to do is to substitute this value into here. And then everything will be down here. And let's do it. This guy, yeah, is become VCC, yeah, and then divided by 2 beta RC. It depends on how you handle the calculation. According to my analysis, uh, you can either substitute the equation with the numerical value, and then quickly you come up with the value of R1 and R2. Either way, right, it will work. Or symbolically, you can also work this out. So, in my understanding is correct, R2 will be equal to minus 7 R1. After some manipulation, yeah, this one will become minus 10 VCC, and then plus 7, and then plus uh, um, 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 10 VCC. Okay, by R1 VCC divided by beta ROC. So this is the case, right? So we found the resistor. Yeah, we just come up with a artificial value for R1 first, and then from there we work out R2. So this is the way how we found the resistance value. Now, assuming that you have no problem with the DC biasing, And assuming that, right, we have you make good use of this equation and we found the value for R1 and R2. So the next thing that you need to do is to suppose now, right, you have the two value R1 and R2 based on the uh, the equation here. Now, what is to be done next? The next thing that you need to do is to do AC analysis. So now, right, we have already done that. Suppose you have no complaint. We need to do AC analysis. So VCC, and then now I suppose after some lengthy DC biasing process, and we obtain the value for R1 and R2. And what is to be done next? Remember, right, the most important thing here is the collector column, and the collector column is given by this amount. You get this value, right, 2cc, right, and then the base column. No matter what, if you have a collector column like this, do you agree the fact that Gm is equal to IC divided by VT? So it will be this value VCC divided by 2RC and then VT. This is the first thing that you have to have. And how about the R log? This is for the early effect. The early effect will be VA, given that the VA is provided in the question, and then IC. So with this in mind, right, so it will be VA, and then times 2RCVT divided by the VCC. So you get this value now. So what is to be done next? The next thing is just to use the conventional small signal modeling technique to work this out. So we are going to work this out. And remember, right, to do modeling, right, what you need to do is just to first substitute this with the small signal model, pi model, yeah. So this one, R pi, and then the current source. The current source is Gm V pi, and R naught, and now the capacitor here will be short circuit. And this one, right, this RC will move to here. So, and this one will become AC ground, and this one will become AC ground. And then if we become AC ground, then we can flip the number, so that we have R1 in parallel with R2. So this is the way how we end up with the network for the small signal analysis. Now, with this circuit, you can quickly find out the output, the voltage gain. So what you need to do is to find this point and then find the sum of the current at this point. So if I do that, we know IC is equals to minus VO divided by this much resistance. Okay, and then this also equals to Vm pi. And what is V pi? V pi is the voltage across this resistor. And ironically, V pi is also equal to V in. I mean, in this case, right? So now, well, we can just say Gm V in. The voltage gain is given by V in. Is equal to minus Vm analog. So nothing is difficult. You just need to find the output resistance, and then multiply by Gm, then you get the voltage gain. And there are many other parameters that you can find as well. The other one that you can find is the input resistance. Normally, we write the input resistance in this manner. So in this case, obviously, very obviously, with the parallel of three resistance, this one, and R pi. When GM can be calculated from here. Analog can be calculated from here, and then you get the voltage gain, and then the input resistance, right? Done is here, and then the output resistance. Right? Everyone know what the output resistance is. This one. So out. Normally we do this to identify the output resistance. In this case, is analog and RC. So this is the basic methodology, and this methodology can be applicable to any similar circuit topology, and you just need to substitute the value into here, and you will get the answer. Now, going backward, we have a homework question. The homework question is not easy to swallow. We have a lot of value here. So I will give you about 1 minute. If you have any question, you ask it now. If you don't, then wait for 1 minute. 2 minutes is better. 2 minutes, then we will work out the solution. I will disclose the solution for the latest homework. Any question? And I will also show you the LT SPI simulation, just to give you some confidence. So apparently, you guys have no question now. Now, I'm going to start working on the homework question. The homework question, right? VCC is equal to 10 watt, and the resistor is 1 ohm, 1 kilo ohm, and we have a device here. Beta is equal to 200, and VA is equal to 100. So this is the device. And now the next thing that we are going to do is to work out the value for R1 and R2. And now, based on the equation here, well, you know the most important value is ICQ1. So IC is going to be equals to um, better do it. VCC equal to ICRC plus VCE, and then you never get wrong. And then minus VCC over ROC, and then VCC, even VCE, yeah? Now we are going to directly substitute the value here. Resistance 1K, 1,000, and then plus 10. This is what we are going to, this is what I kept. So based on the information here, we know the maximum collector current is this value. And 0.01. And the collector current, the operating point, IC, based on this value, right? The optimal one is going to be IC max divided by 2. So the 2 milliamp, and now we need to find IB. IB is going to be IC divided by beta, and then 200. So this is the value for IB, and we are going to use the same trick, right, like what I did before, and you end up with this value, yeah, R1, R2. And then the VCC, R2, and now we are going to substitute each one of these. And remember, this is 0.7 volts. So you have this one, right? VCC R2, R1 plus R2, and this one is going to be IB R1, R2, and then plus 0.7. And now we just substitute the value here. So we have 10, and then R2 and R1 plus 2. And with this in mind, right, then IB and 200 and R1, R2. So we end up with an equation with two unknowns, R1 and R2. And if you substitute R, let's see, I have found one value before. Yeah, if you use R2 is 10K, then R1 by substituting R2 being equals to 10K into this equation, you will end up with R1 equals to 97894. So it's not difficult. It's all done now very quickly. We come up with the biasing network. So in other words, the circuit that we have is like this. R2 10K, R1 9, 7, 8, 9, 4. So this is the so this is what we are going to get. Now, I think I will give you 1 minute, and if you have any question, then you just ask me. So this is the way how we do DC biasing, and you can be in this case, the DC biasing is based on the optimal operating point. But equally, the question would also is also possible for the question to give you the value of collector column IC. So in the exam, if they have dictate that IC is 1 milliamp, right, then you don't work this, you don't go through this analysis anymore. So you don't need to do DC analysis. DC biasing. Okay, now we are going to do small signal analysis. And remember, right, this is the resistance we got. And we also remember the collector current we have is this amount. Now, if you know the collector current, right, so right now we have the resistance value here. We don't have enough space, so if you don't mind, right, I'm going to free up some space. I just need to write down the important value. Based on what we have done after going through a block of power, IC is equal to 5 milliamps, and R1 is equal to 97894 ohms, and R2 is equal to 10K. Okay? Now we can continue. You can continue, yeah? Like what I tell you, right? You just need to V in, V out, and then we just do some quick, very quick transformation. This one, short circuit, and this one, right? R pi, and then this one, right? GM, and then E pi, and then R naught. And then the next step, we flip the upper bound. This one become this one become AC1, and then we just flip it down here. So R2, R1, so it will be R1 in parallel with R2. So 10K in parallel with 97894. So this is the experimental. This one, 10K So you got this, and this one is also over. We have this one here, and then this one will be picked down and end up with RC, right? RC. And we have to work out GM and VT. So it is 0.05 divided by 0.026. So this is value of GM and RO log, the early resistance. This one, this one is going to be VA divided by IC. And IC. So, sorry, this one has already done. And this one is also done. We put it, move it down to here. This one, right? So the voltage gain, VR over over the resistance, R log RC, is equals to GM V pi and GM V in. And from here we know that V out over V in being equals to what? The minus GM and then the resistance R log RC. And R log is this value. And GM is this amount. 0.026. And then R log, which is this one, 0.05. And in parallel with RC, remember, right? RC is 1K. Yeah? This is the value we have used. So if you work this out, if you substitute the value and use your calculator, and you will find that, let me see, let's see. Value here is about 183. So the voltage gain is minus 183. So this is the value that we are supposed to get. And this means if you simulate this circuit in LT SPI, you will end up with this current for the DC operating point. And in the waveform analysis, and you will find out the voltage gain is going to be 183 for 44 dB. So the next thing that I'm going to do is to show you, is to demonstrate to you. We can prove this. We can prove what we have done is totally correct. I'm going to show you now. Okay? Do you have any question?
No questions.
Huh?
No questions.
No question, but no. Okay. Now, what I'm going to do is to show you the LT SPI. So first of all, I'm going to open the circuit. So I'm going to present the window to you. I'm sharing the window to you. So everyone can see the LT SPI window. Yeah, I can also see it. I have already put all these values in here. This is the one I have prepared. So the first thing that you need is to do schematic capture, and you end up with a circuit. And you can connect the capacitor, the full circuit, or you don't do it, right? So you just leave out the DC biasing now. So the resistance that we have is 894 ohm. The R2 is 10K, RC is 1K. Yeah, this is completely consistent with what we have said in the question. And the voltage supply is 10 ohm, 10 volt. The capacitor, it doesn't matter as long as the value is high enough and it will work. And the transistor that I have chosen is 2N22. The reason is in 2N22, I'm going to show you in 2N22, the beta, the value of beta is the value of early voltage is VAF 100 and the beta BF 200. So this is exactly the value that we have used in our large signal and small signal analysis. Okay, so we have chosen this value. Now the very first thing that you need to simulate is to find out the current. If the current is not consistent with what you have calculated, then there's something going wrong in your analysis. Now let's try this. I have told you that first one that you try is the DC operating point. And you just click it here and save it, and you just click run. Then if everything is correct, it will provide a table of all the DC value. And can you see? I see. Yeah, it's 5 milliamp. So this is exactly the same as what we have got in our analysis. 5 milliamp. Okay. Remember, yeah, 5 milliamp. Right? I show you first, right? 5 milliamp, right? 5 milliamp, right? I show you again. On this side, right? 5 milliamp, okay? Now I'm now switching you back to the LT SPI window. Now everything looks okay now. As long as the IC is consistent with what you are trying to get, then everything will be okay. Now you don't need the DC operating point analysis anymore. You can go straight to the AC analysis. I told you, right? The first thing that you need is to create the voltage source for the input. Given that I am still working on the example, right? And the voltage that you are going to use is somewhat here. It doesn't matter what value you put, as long as something blocks zero, it will work. So in this case, yeah, by the way, right, the magnitude has to be positive. 10, we can use 100. It doesn't matter, right? So we got this, and everything is okay now, right? And we use AC analysis. AC analysis means small signal analysis, and we use linear, okay, 100, and then the starting frequency, 1 hertz, at least 1 hertz, yeah, it can be higher, and the stop frequency, right? Any large value, large enough for you to visualize the output is good. So I will just use 100K, okay, or even 1 rand. I'll put it here and simulate it. And now you right-click the waveform window. Now right-click your mouse in the waveform window, and then choose Add Trace, Add Traces, okay? And then you have 2 voltages, output and input. Just do it, and then put a backslash here. This means the output voltage needs to be divided by the input. Okay, so now you got the output now. The waveform is very clear. It's about 44 dB in terms of gain, and I'm going to show you the linear value. You will be surprised. Can you see? It's exactly 180. Our answer is 183, and the answer here is 180. So what we have done is totally correct. Exactly. It's consistent what we expected. So do you have any questions regarding this simulation? Hello? No question.
Yes, no question.
No question from you. How about the rest of the class?
No question.
You can't maybe sleeping now. I don't know why. Okay, the next thing that I'm going to show you is I have shown you the DC operating point analysis in LT Spice, and I have also shown you the AC analysis, and the AC analysis end up with this frequency response. So what I have not shown you is the actual waveform. The waveform. Now I'm going to show you. Suppose we are using the same circuit. I want to look at the actual waveform. So this is the circuit. So what do? We raise this voltage source. Originally, your voltage source is the AC voltage source, but you don't do this. You use the time domain. The time domain voltage source is on your left-hand side. So there are many choices you can get. You can choose pulse. You can choose piecewise linear voltage. You can even choose exponential one, which is something very typical one. S, F, F, M. Don't know what it is. I don't know what it is. Right? This is a new one. And the most important one is sine. This means your input voltage is a sine wave. Sine wave, right? So you in different value, right? You have different options to build in. If you choose this one, when you are this, if you choose this one linear, then you have to key in the value at different times. And if you choose sine wave, right, you need to fill in at least the amplitude. The next thing that you are going to fill in is the frequency. With these 2 values, that will be enough for you to work this out. And now, how are we going to do AC analysis? So we just do 5, and then we should pick transient. And you need to put the stop time. Right now, I don't know the best stop time I am going to use. I just randomly choose, say 10 milli. Yeah, this may not be a good value. So I get on with a transient analysis here. So another thing that I have to remind you, not every spy simulators, not every spy simulator is equal. And most of the spy simulators have convergence problem. LT spice is not an exception. So in order to achieve convergence, you have to use some sort of trick. The trick that I use is to put this value, right? You have to kick in uh, spy directive and then put option G mean and then put some value here. I use -10, right? So this is the way that I do, right? So you put the spy analysis here. So this one will have to achieve convergence more quickly. Now I'm going to simulate this. So if you have done everything correctly, then you immediately finish the simulation. And how do we know the simulation is done? You click on the simulation tab, and then you find out all these pulse, how clear waveforms, all great, all gray out, not applicable. Graying out means not applicable. Okay, so this means the simulation has been correctly done. Now we are going to simulate the window. You just right click your mouse over the waveform window and then choose add trace. So this time we are not going to plot the waveform. We are going to plot the actual voltage. The first voltage that we are going to plot is the input voltage. So this is the input voltage. It's a little bit the time period is a little bit too long. So I'm going to shrink it to 1 milli. Right? So the waveform of the input is clearly a sine wave. Then output. So I'm going to plot the output as well. Remember, right? The input is green. Yeah. And we are going to plot the output. The output is blue. The input is green. Yeah, green is V in. The blue one is the output. So you can see that the voltage of very small sinusoidal voltage can be enormously amplified using this thing. So you can see the amplifier is very powerful. It can just easily amplify and very weaken the signal into something huge. So now I'm going to show you. I'm going to make it more visible to you. Right? I'm going to lower the amplification factor. So now with the 100K. Let's say 1K, right? 5K. Let's see. Not very good. 20K. Worse. 8K. Oh, anyway, I think we have done enough. It's still difficult for me to come up with the right value. Yeah, I mean, I'm trying to show you the waveform. So your circuit is here, and the waveform is here. Right, the input voltage is just that much small, and you also need to know that. Yeah, maybe we can just reduce the voltage. Reduce the voltage to 8 volt, and hopefully still very large. Still very large. Oh, anyway, I think for this circuit, I think we have already done enough. I will give you about 5 minutes to digest this question, and then we are going to step into another topic. Yeah, take 5 minutes break. 5 minutes, and you can try yourself. You can, if you are sitting in front of the computer, you can try simulating this circuit. The circuit is here. Okay. So with this circuit, you can amplify the input signal, and the output will be significantly amplified the value, significantly amplify the waveform. Okay, 5 minutes, right? We'll take about 5 minutes break. We will come back in about uh, 2:15. Yeah, we take about 5 minutes break, right? And then we will come back again. Okay, we are going to step into another topic, and we have a lot of things uh, unfinished. Now, previously, you have learned the common emitter amplifier. This is the typical one, and today what we are trying to do is to extend the analysis. So the new topic, um, yeah, maybe we'll talk about the other thing first. Sorry about that, yeah. A T model. Uh, we have previously learned something so-called pi model. Um, there are situations where pi model is not effective. One of the cases is if you have a resistance in the emitter, then pi model is a very difficult thing to work with. What I'm going to tell you is, can we not just move this resistor from here to here without changing the property? So the property is you need to make sure the voltage V pi will maintain the same value. Yeah, V pi, right? If you look at here, this is V pi. The so-called V pi is here. So by moving the resistor, moving this value, we are going to just short circuit here, and then we move something into here. So this is another model that we want to run, and this model is so-called T model. T model. Now let's take a look here. V pi, what is V pi? V pi is IB times R pi. And R pi is equals to beta divided by GM. And if you look at here carefully, beta times IB is IC divided by GM. So if IE is approximately equals to IC, so this means this is IE. This means we can just move IC and then times the resistance value GM into here. So this is the so-called T model. T model. And I'm going to show you how we can use the T model to work out the analysis. So for the time being, I presume you have no problem this instruction. We find out what the resistance originally have the value alpha here. And by moving the resistance from here, from this branch into the emitter branch, and we end up with another resistive value here, 1 over Gm. And here to the base will be short circuit to here. So this is the so-called T model, right? You know why it look like the T sign, okay? Other thing will remain unchanged. By the way, arrow log should be connected up to this point. Sorry about that. You connect it up to this point because arrow log is the resistance between C and E, not up to here. So, so this is the T model that we are going to be focused on. And I'm going to use this T model to illustrate an example to you. So suppose you have the value and RC and then ROB, right? So your output and input will be formed like this. And now this is your circuit. Like what I said to you, but you need to substitute the transistor with its small signal equivalent. But the small signal equivalent, previously, well, you only know pi model, but now you have some more knowledge about this topic. And you can also use T model. And the T model is very simple. You just like this, and then this is IC. And here, short circuited. And analog. And remember, right? You have GM, 1 over GM. So it's much easier to use. Much easier to use. I'll tell you why. So now you are going to turn this into AC1. So this one will be flipped down. And this one will be flipped down up here. So everything becomes easier now. So why do I need to? Why do I say that? Right? The reason is very simple. Now VL divided by this resistance. We will consider this is the current IC. IC is equals to the output voltage divided by this resistance. Okay? Now, how about the input? If you look at the input here, right? Input is the voltage here. And I just want to know the IC. We know the voltage here at this point. The voltage at this point is still Vin, yeah? So if you want me to tell you, yeah, the current at this branch, the current at this branch is E voltage divided by the resistance. Okay? And because this one is similar to IC. So you have equation 1 and equation 2, right? And you have something like this here, yeah? So, what do we do? The next step is, right, equation 1 divided by equation 2. IC, right? So V in 1 over Gm. This one is exactly equal to this one. I'm sorry. So it's much easier to use. Right? For some reason, right? This one is easier to use. Okay, I will give you 1 minute to digest it. Right? This is another way to solve it, to solve the problem. So this is so-called the T model. T model. In many cases, T model is easier to use, but it's not always true. Okay, now we are going to, I've assumed you have no problem with T model, yeah? If you have, then we just need to do some homework exercise. After doing some homework exercise, you will know what to do. Now the next thing that we are going to look at is another new topic. The topic is common emitter amplifier with emitter degenerator. Common emitter amplifier with emitter degeneration. The so-called emitter degeneration means you need to add the tail resistance. Now what I'm going to show you. Previously, I have shown you the amplifier like this. It will work for all examples. So this is the previous one I have shown you, and this is the ordinary common emitter amplifier. The common emitter amplifier with emitter degeneration means this one in the tail, you need to add a resistance here. And this means you need to do this. So this is so-called common emitter amplifier with emitter degeneration. And the circuit is not easy to resolve. I can tell you, this is the reason why the electronic course is not as easy as many people think. By just adding a small resistance here, the whole circuit becomes very complicated. And this is the reason why I'm going to show you in these lectures how to resolve this problem. So now I'm going to show you how to use T model to resolve it first. And for the time being, we are going to ignore the early effect. Because if I do that, then it will be very difficult for you to capture. So the first thing you need is to replace this. I'm going to so the first thing is to replace this with the T model. The T model, and then 1 over Gm, and then the P terminal. So this is the network. And the next thing is to short circuit the capacitor. And then the next thing is to now I think everything will become automatically downhill. Why? If you just look at the current here, IC is equal to the voltage divided by the resistance. ER divided by RC. In this case, and we don't forget, it is minus, okay? And now, so this is the current. Now we'll take a look in this point. Assuming that the current IB is just too small to consider. So IE is approximately equal to IC. In this case, and what is the voltage here? The voltage here remains V in. V in, right? This is short circuit, short circuit, short circuit, short circuit up to this point here. V in, right? So V in divided by the total resistance here. RB plus 1 over Gm. So with this in mind, right, you can just equate these two equations. Minus VR divided by RC so based on the information here, you can quickly work out the voltage gain. The voltage gain based on information I have here is RC divided by RB. But normally, it's difficult to realize that. First of all, we need to make sure we have some understanding of the circuit. First of all, right, if you take a look in this equation, you have 1 over Gm here. 1 over Gm is, it depends. It depends. If 1 over Gm, if 1 over Gm is reasonably small, it's difficult to tell whether it's small or large. So then the voltage gain, which is given by this formula, will become RC, minus RB. So that's why, right, you don't really need to know the exact transistor. You don't really, now, right, in what situation where this amplifier, where this formula, this trait is usable. 1 over Gm is small. Another situation is, so, or if RC and RB are large, huge, right? Several kilo ohm, several mega ohm. If these two values are large, then we can just say by justifying here, V out over V in, which is originally we got this RC, and then RB plus 1 over GM, right? But now, 1 over GM, is GM itself is a conductor for a transistor, and different transistor will have different value. But now I've forgotten all these transconductor. So if RB is much larger than 1 over GM, so if RB is much bigger than 1 over GM, then we can say the voltage gain is minus. So this from here, what does it mean? Sorry. Yeah, I made a mistake, right? It should be RE. Oh yeah, RE. Yeah, RE. Oh my God, I make a mistake for so many. I shouldn't move so fast. So you can see that if the value of the tail resistance is large, then you don't really need to know which transistor you are using. In the old day, the engineer the engineer who repair the television, who repair the radio, have almost zero knowledge about circuit analysis. They don't know all these equations. They don't know all these formulas. Nothing, right? But they are very efficient and they are very capable. They can repair your radio. The reason is because they know this trick. If you have a resistor here, so they just substitute any transistor, just unplug some of the transistor from the broken radio, and then just try it, see if it will work. And then if it work, good, then they will charge you money. But they themselves doesn't know whether the value are correct or not. The reason is because the transistor doesn't really matter. You just need to make sure you have this. You make sure RE is much greater than RM, 1 over GM. Then your job is done. So to so first of all, I'm going to show you an example. I'm going to erase this part. Yeah, I'm going to erase this part. We have all the recording. Right? You don't need to worry about you don't need to worry about missing any information. So now let's try one circuit, right? If you have a circuit like this, the VCC is 10 volt, and for the time being, I'm going to use because we are now using emitter degeneration. So let's say this is 10K, and this one, I told you before. says that this one is 10K, yeah, make it large. And this one is going to be 90K, yeah. So you may be given, you may not have the value for beta, you may not have the early effect. It doesn't matter. Uh, this value is absolutely large enough compared to 1 over GM. In most cases, this is true. So if I am the designer, I automatically know uh, the, the ratio, the uh, voltage gain is RC divided by RE. So 90K divided by 10K. So it's about 9. So you don't believe that? I'm going to show you. So that's why if you don't have any information about the transistor, and you pick up any radio from the garbage bin, and you just want to make it work. So the easiest way that you can do is to make sure the resistor are still functional. If it does, then you just erase the transistor, then it will work. So repairing a radio is not something very complicated. Now I'm going to show you an example. So now you are looking at the LT spy window, and I'm going to show you. And this one is called RC. And this one is called RP. And this one is 10K, 90K, and this one is 10K. And you will be surprised. The So I'm going to use the same transistor. And I'm going to do a very simple biasing. Say here, the biasing is 90, 372K. I hope this will work. So Now the circuit is very complicated, but because of your adding the tail resistance, then the way how we approach the problem will be different. And if I do simulation, V1 Tango and uh, the analysis. So let's try this. So this is the new circuit, yeah? And we are going to simulate this. And we have to do this window. And let's try, sorry, wait, I have to label, out, in. So we are in. So we expect the amplification should be around 9 volt. 9, yeah. It's not as simple as structure. 9, maybe the value is here is the problem. Yeah, let's try this. Okay. Okay, we need a bigger value. Okay, now can you see the amplification now is 8.5. 8.5. 8.5 is nearly 9. All we need to do is to have a right value. You need to, I remember when I was young, one professor from an American university had demonstrated to me how a transistor works. And he actually used the finger to replace this transistor. He used the finger as a resistor. And then the voice was significantly amplified. So this is the way, and if the resistance is large enough, then it will work. Let's see if we add one more zero here. No good. We have to have a white value. Yeah, anyway. Okay? I hope you know, yeah, I mean, we just need to design the operating point. We know how to do it, right? But anyway, I have already shown you the trick. Now the gain is almost 9, and this is the beauty. You just need to substitute the resistor, the ratio RC to R. Sorry, this is RE. RC divided by RE is the voltage gain. So uh, so this is something. If you don't know anything in examination, you may just say everything is approximated. This one is approximated. The value is about 9K divided by 10K. The answer is 9. So, okay. I am going to switch you back to so this is the beauty of emitter degeneration. But the fact is, the actual value is not that simple. The actual voltage gain is, this is just an approximate value. The actual value is RC divided by E plus 1 over Gm. So this means you need to have the proper value. RE and then plus VT divided by IC, which is the collector current. So in this case, the smaller the collector current, the circuit will work better. The most. This means the resistor here should be as much as possible, as large as possible. So RB should be a large value. So in case if you are assigned to design the amplifier for your boss, and they want a solution from you in no more than 5 minutes, right? Then this is the one. Okay. Now the approximate one is done, but in actual fact, there is a lot of things to consider. You cannot just say, well, everything is approximate. Yeah, that's good, right? For approximation, you got this. You also need to consider the effect, so-called early effect. And unfortunately, with early effect, you cannot use the T model very easily. In these lectures, I'm going to show about the common emitter amplifier with emitter degeneration to you in a proper way, in the traditional way. The traditional way is the way that is the log the T model way. We are going to use pi model to solve it. Okay? So stay tuned. So our shortcut is like this. We have RC And you may have some bias in that one. It doesn't matter for me because at the end, we just need to calculate it. Sorry, I need to replace the pen. I don't want the pen to spoil the letters. Give me a second, yeah? Now, so we are going to solve the problem in a traditional manner. So the input and output will be short circuit. The capacitor will be short circuited. So and this one will be replaced by pi model, yeah? We are not going to use T model. I told you it's difficult. So we use pi model. And this one, so to begin with, let me see. First, right, we need to just convert this. This one also. So let's, for example, we have no RB and RC. Let's make it simple. And we are going to, should I do that? Yeah, maybe just leave it first, right? We just have shown we have this case. Your amplifier is like this. So in this case, the output has to have RC. So let's say, right, we have a circuit like this. So V in and then V out. And this is the circuit that we are going to analyze. So now, you have a circuit, and how are we going to tackle it? I'm telling you, this circuit is very difficult to be solved. Just by adding one resistor here, and you just spoil everything. It looks easy, but actually it's not easy. Many students have tried it before. They cannot do it alone without my help. The reason is this so-called degeneration is really degenerating, depressing. So I think the very first thing that you need to do is epsilon IB, IC is approximately equal to E. This is the basic assumption. And this value is much, much quicker than IP. So essentially, when you consider the circuit here, you might just consider the voltage here, Vx, and if we are going to resolve this, what I would do is, uh, we have a current source here, and we have a resistor here. So if I am going to solve the circuit, I will just I will just uh, uh, I've shown the current being very low. So this means for the time being, we treat this as the open circuit. And we have a Vx here. Okay? Vx, that doesn't matter. And now we just use this network to work out. Now you have a parallel combination of the current source and the resistor. Can we make it like the Thevenin equivalent? Right now it's Lofton equivalent. Lofton network. You just work it out, and then so this is the voltage source, and this one Vx. So now, what is Vx? If the current here is IC, the current here should remain IC approximately. So we have a few pieces of information. Let's connect this back first. Uh, First, let's take a look in the voltage V in. V in is equals to the voltage here, IP times R pi plus Vx. Vx is this value. But you can see that is IC times RE, okay? So if you just continue with the analysis here, IB, what is IB? IB is IC divided by beta. I'm also running out of space. Sorry. Let me just do it here. V in is equal to IB R pi plus IC RE. And if we do that, right, IC is what? Beta and R pi plus IC RE. And what is R pi? R pi is beta times GM. So this term here, right, IC divided by beta R pi is equals to IC and then beta times GM, right? So beta and cancel out with each other. So you end up with IC divided by GM. Okay, so let's continue. Yeah, you don't need so much information, right? So is IC and then 1 over GM plus RE. So this is the number one important piece of information. The VE is actually equal to this one. And how about VO? VO, well, we can work this out. VO is here, and uh, we have made this assumption. This current is much greater than IB. So for the time being, we can just assume it is the open circuit here. Assume is not exactly open circuit. It's Vx, right? Without the current, this Vx will not be there. So now we are going to work this out. What is V out? V out is going to be the voltage drop here, IC times R, and this is another voltage. The current goes down, so there is a minus here. Okay, sorry about that. So minus. All right, current goes down. Current short.
Mr. Yi.
Yeah,
Mr. Yi.
it should be minus.
Mr. Yi.
Okay, and then you will add IC times RE. So now you can see that we are now getting there. In what way? We at least we know we have a value IC here, and we have V pi. So what we are going to do now is to substitute this value V pi first. Yeah, we have to do it step by step. Otherwise, mistake will follow. So IC remain. And then GM. And then we'll move this one to here. And then V pi. V pi is what is V pi? V pi is this value. V pi is IB times R pi. But we have already done that, right? V pi IB is IC over beta, and R pi beta over GM. So essentially, this is IC divided by GM. Okay, so I will just replace this with IC divided by GM. But hang on a minute, you have a GM here, so it cancels off with each other. Okay, now we are now heading to something easier. Yeah? I think there's something wrong now. IC times this value, and then the voltage V pi, which is this one. Yeah, this is correct, and this is correct. Yeah, this is correct. Yeah, let me just check. V pi. Yeah, we can just replace this for the time being, right? IC, and then we just keep this value. And then we try this way. We pi, right? We use the other way to, we use this voltage minus this voltage. Minus IC. I hope it will work. So if you further simplify this circuit, this yeah, I hope. Okay, now it's getting clear now. If you further factorize this term, and then so before going forward, we need to realize one thing. Uh, this value here is, and this value uh, 1 plus GM is a very small value. GM is a very small value in this case. This one minus this one. So essentially, we can just remove this term. Now, I think it's now, actually you cannot do that. You cannot do that. Okay, I'm going to substitute IC with this value. Yeah, in here, IC is equal to
Dr.
V.
Liu,
Yes?
why we don't multiply R not parallel with RC with CM and CRE?
No, no.
The second line from the bottom.
The second line from the bottom.
CM and CRE. Yeah, we should multiply it with R not parallel with RC.
Yeah, let's start from here. Yeah, V out is equals to IC times this one, and then the voltage GM V by multiplied by this, and then add one here. Uh, and this one is like this, and then V in. I don't know what strategy is the best. because you just need to substitute V pi here. If you do this, right, then it becomes very complicated. Yeah, forgive me. Yeah, let's think one more step here. I know it's very difficult. There is no textbook talking about this. V pi, V pi, V pi is equals to IB times R pi. R pi is equals to beta over GM, and IB is equal to IC divided by um, beta. So essentially, the value, right, we don't really need to have so much complication, right? IC divided by GM, right? So I think this is good enough. IC divided by GM. But then you have a value here. You have a there's something wrong here. Yeah? The current goes this way. Yeah, there's nothing wrong. And if we just continue to do this, this one cancel off. And if you cancel off, then we will end up with V out being equal to IC times RE, but that doesn't make sense at all. Yeah, give me about a couple more minutes. Let's try this. Hang on a minute. Yeah. I need to look at the notes. More on output resistance. RE. Emitter degeneration. I didn't have this in my notes. Okay, I didn't have this in my lecture slides. I just suddenly come up with a solution in pi model. I know it's difficult to resolve in pi model, but it's easy to resolve in T model. Well, let's see. I know what happened now. We cannot do this because RC is directly connected to the ground. Hey, my God, almost. I was also fooling myself. Okay, So the circuit is like this. Hi. The circuit here is okay. The circuit here is okay. But the actual small signal diagram was wrong. The RC should have another end connected to the AC ground, not to here. I will make a mistake. Okay? I mean, I make a mistake here. Originally, it's like this. It's like this. I make a mistake. I should not connect these two points together. Okay? So this is the mistake, right? There shouldn't be any term like this. No way. So we just leave it. Okay? So this is the real second. Now the next step that I would suggest is to use taperized checkers to solve it. So if you do that, then you will have minus GMB pi R naught and R naught here. Now I think it's becoming much clearer now. The only thing that is not quite clear is this RC, but we can isolate this. We can just take a look in V pi here first. So V out is equals to a few components. One is IC, yes? IC times R out. The other one minus GM V pi R naught. And the other one RC RE. I think this one is much clearer now. And V pi, what is V pi? GM V pi, V pi is equal to GM V pi is equal to just IC. So we just still doesn't make sense. Doesn't make sense at all. Because you have a voltage drop here, and this one is here, and let me see, right? If you use this value, substitute to V pi. I see. And you have only IE left. So all you have proven here, there is no voltage from here to here. Does it make sense? It doesn't make sense at all. V out divided by IC. Okay, anyway, we just do it in minus IC RC. We just avoid this loop. So V out over V in. V in is like this, V out is like this. So again, so you end up with something exactly the same. Yeah, I'm not going to do anything further. Yeah, you still get the same formula like what we did in pi model. Do you know what I'm talking about? I don't care about this level. I just use this branch, and then I end up with the same formula. Okay, for the time being, right, we have the further understanding of this so-called common emitter amplifier with emitter degeneration. I have already shown you the simulation. The simulation have proven this formula. And now we are going to step into another topic, common collector amplifier. And let's see what time we have. Yeah, we have plenty of time. Now, this topic is half finished. Is decided to be like this. There's nothing wrong here. There is some remaining issue associated with this topology, but this is not the right time to continue. I am going to tell you later. Right now, we just focus on this formula. RC divided by 1 over GM plus RE. That's all you need. Now, another thing that I am going to show you is, if we elaborate, you further expand this level, V out and divided by V in. You will notice that, right? GM RC, and then RE 1 plus GM RE. In the past, if you remember my lectures, you will know that the voltage gain used to be minus GM and then times the big function value. Normally, right, is the RC and then in parallel with the level, with some other value. But now the voltage gain is scaled down by 1 over 1 plus GMRE. So can you see the difference? This term is called transconductance. And this term, yeah, if you look here, yeah, we will find out that transconductance is essentially scaled down. It becomes a smaller charge. The transconductance becomes smaller by this factor. Originally is GM. The new one is GM1 divided by 1 plus GMRE. So at this stage, you only need to know this thing. Now, about this topic, right? Now you know the voltage gain. And how about the input resistance? The input resistance. Yeah, obviously the input resistance is but anyway, for the time being, right, I've already proven to you using T model and pi model and the resistance and the value is correct. Now I'm going to show you the input resistance, how the input resistance is calculated. And the good thing about this circuit is that the drop, the weakness of this circuit is the gain will be lower because of this scalar down effect in the transconductor. But on the other hand, the input resistance here is enormously elevated. We want the input resistance to be high. Now, consider another one, the input resistance. The input resistance, you consider the voltage here, the input voltage here. V in is equal to IB divided times Ry. So this means the voltage across this resistor. And then the voltage across this resistor. So if we just analyze this, and knowing that IB is equal to IC divided by beta, then if we just further elaborate it, we end up with this amount. So we have, yeah, no good, no good. We have this amount, yeah, IB, and then R pi. And we know IC. IC is equal to IB times beta, RE. And we factorize this and take off IB from the bracket. So we get this value. We get this value. Yeah, let's further elaborate this thing. Immediately, I know what is R in. R in is equal to V in, the voltage divided by the current. Okay? So based on the information here is R pi plus beta RE. But this is not enough because this is not clear to you. So I'm going to elaborate this. Further divide this circuit. R pi is beta divided by GM. And RE. So now it's becoming clearer now. Beta and then 1 plus GMRE over GM. Okay, now it's clear now. Beta over GM is R pi. R pi is the original value. And you have to scale it up. So the voltage gain is equal to 1 over GM and then 1 plus GM RE. And then the resistance value. But now taking a look here, R in for an ordinary common emitter amplifier, the input resistance is R pi. But with the tail resistance, we become R pi and scale up by 1 plus GMRE. So this is really interesting. And the next thing that I am going to tell you is that something else. For the time being, there is one more issue here. Another issue is output resistance. And I'm not going to tell you now. There's the reason. We have to go through the same kind of analysis, which is also possible. But we just stop for a while. We actually we can continue. We can continue. So now the input resistance based on what I have calculated is R pi times this value. The voltage gain is this value, and they all query this vector 1 plus GM times RE. In this case, for the input resistance, the input resistance got scaled up and the 1+GMRE is at the top. But in the case of voltage gain, 1+GMRE is at the bottom. Now, what I'm going to do is to work out the output resistance, ROut. So if you don't mind, I'm going to erase it. Yes, we are going to do something hard now. We are going to do something hard. Yeah. So let's say our job is to find out the output resistance here. Say this one is our pump. Yeah. So now, how are we going to do it? Right? So we just keep this value, right? Keep it. We just use the always, yeah. Forget about the RC, and let's try this. We out is equals to the voltage drop here. Yeah, I still trying, right? And then the voltage Tm, V pi, and R, and then this value. I hope this time it will work. Now our job is to find out our pump. We want to find out the output resistance due to this RE. And theoretically, we need to, this our pump should be equal to this voltage divided by this current. So this is our job. So we need to solve this equation in a way that we can calculate VL divided by IC. And let's see if we can do this. Now we have done this, and then V pi, according to here, is V in minus ICRE. I hope it will work. Usually pi, if we substitute into here. Yeah, let me check the note first. Check the note first. It's doable. Bx The way I use is different. Maybe substitute this to here. Then we will have a V in. Yeah, I know why now. The output resistance, when we calculate the output resistance, we need to short circuit the input. And then let's talk about that later. Yeah, this is an entirely different topic. If you look into my lectures notes, we have a separated handout about this. I was trying to push harder, but then I got stuck here. Okay, now let's step into another topic. Yeah, the problem can be solved, but we need some extra knowledge, some additional information. The way how we calculate the output impedance is to sort the input first. So the input, we have to short circuit it, and then we calculate V out divided by IC. And we will talk about this later. So the topic about emitter degeneration has been done. Yeah, we will talk about the output resistance later. Now, another thing that I want you to know is common collector amplifier. So what it is? So we basically need a functional transistor. The transistor has to be biased to the active region. So if you have a IC characteristic, you have to bias it somewhere in the middle. So you want the kill point to be here. So if you do biasing, right, this will be the circuit you want. Sorry, this will be the circuit you want. And we don't use any collector resistance. This is so-called common collector. Remember, I have explained to you the word common means ground. So the collector here will be grounded. So you end up with a resistor, and we use the resistor RE. The emitter is not grounded. And this is the so-called common emitter amplifier. And where is the output? The output is not to be tapped here. It's raising from clamp. It's not correct to tap the output from here. Instead, it tap the output from here. And now, and what is the good thing about this circuit? And before going forward, we need to find out DC biasing first. The DC biasing is to be done in the same way. We bias it, use whatever technique you have. So, for example, you bias it using the fixed space technique. And the input is to be isolated through a capacitor. And the output is to be tapped at this point. And now we will examine what kind of voltage gain you will get. So you need to use the biasing network, or RB will be decided in a way to make sure IC is in this point. Okay? So if you just look at the network here, RE and IC is equals to VCC minus D. And with this in mind, so you just need to use the same way. So for optimal biasing, you should end up with what? VCC divided by 2RE. The voltage divided by choice as the tail resistance. So this is the current, the optimal current. And if you want to design the network or the base, then the value to start is ICQ. So I presume you have no problem with this. I'm not going to talk too much about the DC biasing. But instead, I'm going to use the small signal parameter. And I'm going to show you what you are going to expect from this circuit. So now, capacitor short circuit. Input short circuit. And VCC is the AC ground. So this one will move down here. And now is like this. And this one is short circuit. So first of all, we place this as a small signal model first. So we just use the pi model or T model, doesn't matter. So we use the T model, pi model, right? Pi model is easier to use. So we do that. Actually, T model is easier. Just use T model. We do this, and then we use the current source, which is IC. CM, and we have another resistor here, RE. And the output will be tapped here. So this is the common collector amplifier. I'm now using T model to resolve it. And what is now where the current go through here, right, which is also IC. And this one is V in. And then this one is V out. So now, do you recognize this? The V in will go through a voltage divider, and you will end up with V out. So basically, V out is equal to V in times RE, and then divided by the voltage divider. So if you want to know the voltage gain, then this is the voltage gain. Now, in the previous topology, we have RC divided by RE, but now is RE divided by something similar. You divide it by this value. So if RE is much greater than 1 over GM, then V out over V in is equals to what? Is equal to 1. So there is no amplification for this amplifier. Do you know why? There is no amplification. So what is the use of this circuit? Can anyone give any suggestion? The V out over V in is almost equals to 1. Why do we want this? This circuit is very important. Why do we don't want this? Can anyone explain to me? Hello? Why do we need a volume? This is also so-called amplifier, and it is frequently used. And why do we need to use this kind of device in the circuit? There's no amplification at all. The amplification, right, you calculate it here, RE divided by RE plus something. But this value is normally very small. And eventually, you end up with something very close to 1. Why do we need this kind of thing? Hello?
I think to be able to transmit electricity further.
To be what?
To transmit the electricity further.
Okay. Thank you for your input, but the answer is no. The answer is not in the amplification. Not everything is about the amplification. The answer is the input resistance. The input resistance of this circuit is very high. Now let's take a look in the input resistance just by looking in the circuit here. Now, you take a look here, the input resistance is just by direct observation. Is RB in parallel with 1 over Gm plus RE. So it is RB in parallel with 1 plus Gm RE and then Gm. So by adding a resistance here, you enormously add up the resistance at the input. So what you can do is, no matter, one of the problems is when you have an amplifier, you cannot use the low resistance load. Say, for example, right, the load is 50 ohm. If you do that, then the amplifier will be burning hot. You have to use a very, very large value at the output. So if you want to drive the low resistance load, what do we do? the easiest thing is to use this kind of amplifier. And this will work. And you can use 50 ohm, doesn't matter. So by adding this little box here, yeah, by adding blocks here, then you will be able to drive with video. And I'm going to show you what I mean. And then we will step into one more topic. And the timing is very well controlled today. Right now, we are only 20 people. What happened to the rest of the class? Still too boring? Anyway, I'm going to show you LD spy. Now you are looking at the LT spy window, and I'm going to show you the program of common emitter amplifier. And like this one we have. So this is the circuit that we have played with. Now you are not driving any load. Suppose I connect a resistance here at the load. And the resistance, right, could be a 3 ohm. It could be a electric iron. The resistance is no more than 50 ohm. This is normally is 100 ohm. So originally, without this resistor, you have a very good gain. The output over input is almost 183. But now, if you connected the load with connect the output with a very low resistance, and I show you, what do you get? The gain is only 16. There's no gain at all. When you reduce it to 50 ohm, no gain. So how do we fix the problem? And this is the reason why I want to show you. I want to teach you this topic. This is so-called common collector. So how are we going to do? We take the whole circuit and we instead of driving R3, the output resistance directly, we add another block here. And this block is so-called the same transistor. Yeah? We can use another NPN. And is the common collector amplifier. And at the tail, we need a high resistance. Normally, you need about 10K. The higher, the better. The higher, the better, yeah? I'm not telling lie. So we can have, say, 100K. So now you can drive the resistance. So with this simple setup, you can drive the resistance. The resistance will be the low ohmic resistance. Yeah? Yeah, we can try it. Now your drill is just has only 50 ohm in terms of resistance. So let's try this. And the output is here. And I will put 50 here. 100 first. And see if we go maintain the gain. Now, yeah, no gain at all. No gain. Yeah. No gain means no current. So what can we do? Because the circuit needs a little bit of current. So I told you about the resistance here. As long as you have resistance here, you work. So you don't need to rigidly put just a resistance. You can add some value like current source. Current source. And the current source is, for the time being, right? I just put current source. Yeah, the theoretical value for current source is the resistance of the current source is theoretically infinity. Okay, I just put it here. And here I say 10 milliamp. Now go to it and run it. Maybe there's something wrong here. Now it still doesn't run, but it's better. Originally we have 660 micro. This is too low. This is just almost 1. So what we can do is we further increase the value. We increase the value to 100 milli. Now, can you see? It's now getting better now. And if we increase it further, say 10 ampere. So now, right, it's now better now. So you can just, it's up to you to increase the value. And I also have a mistake here. We don't really need this. I can just step it to this. Now, can you see? The gain immediately increase. And if we use the 1 milli and see if it works. Okay? So, do you understand the idea? I restore the gain. Right now, you are now driving a low resistance. But I can do this. Even the ohmic is just 100. too small. I can still maintain such a large gain. Now, how about that? Reduce it to 50. Would it work? Yeah, it's still working, but to a lesser extent. But I can say we reduce the current, say make it 0.1. The lower the current, the better. Yeah, whatever. Yeah, it's similar. Yeah. I forgot that the current should be a little bit high. Yeah, whatever. This is the maximum I can get. So, in order to get a gain, you have to use a device, and this device is this transistor, this amplifier. Then this amplifier is called common collector amplifier. So this is the one. Common, the meaning of common is ground. The collector is grounded. So I am going to switch you back to the whiteboard and further explain the significance of this amplifier. And you don't need the presentation. Okay, I'm going to continue. And let's see. I forgot to show you one more thing. Let's see here. I forgot to show you one more thing. Yeah, sorry about that. I need to show you one more thing. Let's try this. Yeah, I'm going to show you one more thing. I told you why we need a the current source. I was trying to fit the one. But do you really need this current source? I can just show you. Now let's just use 100 ohm. Do we really need that? The answer is probably no. Now can you see? Can you see when without the current source, it will equally works. With a current source, it just works better. Okay? So you still have a lot of gain. The most important thing about the amplifier is the gain. And in this case, with just a simple driver, simple common collector amplifier, you drive a low resistance output. Low resistance output is very difficult to drive, but you can do that with this simple amplifier. And this amplifier is so-called common collector amplifier. Okay? So now I just stop presenting, and then I will switch you back to the whiteboard. So the key is you don't need any current source here. You can artificially use the current source, but you don't need it. This device is very important, and you will find out. You will find out all Indian or all other company. They use this device in almost all the circuits. Right? They use trillions of this device. They use trillions of this device. And this is so-called common collector amplifier. Amplifier is a misleading term because there is no amplification at all. And you can add a current source, you can you can be without any current source, it will equally work. The correct terms, because the amplification is always one, the correct name for this amplifier is called voltage follower. Voltage follower. Whatever input you have, the output will be the same. The key of this amplifier lies in the input resistance. And voltage follower is also a misleading term because it doesn't tell you the real purpose. The real purpose of this device is to drive a low resistance load. So as such, this circuit is also called a driver. Voltage driver. Voltage driver is a driving circuit. Or buffer. So all these terms refers to the same thing. Common collector amplifier. Common collector amplifier is not an amplifier. It's a buffer. It will bring up the power because the load may be too. They have too low resistance. For instance, 20 ohm. But with a buffer, it will work. And as you will sure notice, in the integrated circuit, almost all the bond bank have this circuit. So this is the integrated circuit. All the circuits have this device, like the buffer. So I hope this is clear enough for you. Do you have any other question?
No question.
You have no question, right? How about the rest of the class? So this is not a view amplifier. The voltage gain is 1. There is no amplification. The main purpose is not for amplification. It is a driver. It's a buffer. It's also called buffer. Yeah, you know? Have you heard of anything? Buffer in a microprocessor. There's a buffer, right? But the so-called buffer is like this. And in almost all the digital circuits, we will need buffer, driver, voltage follower, whatever you like to call, right? It is the kind of driving circuit to drive the load. The circuit, the amplifier itself is not strong enough to drive the low resistance load. You need this kind of circuit. So this is one advantage. Another advantage is, remember, when I fiddle around with the schematic, I have eliminated this capacitor. And the capacitor, do you know what capacitor is? A large value. In IC, in the integrated circuit, it's too small. Integrated circuit is just that small. It cannot accommodate a big capacitor. Impossible. So all this device here is destructive. If you add the device here, you won't be able to sell your chips. The good thing about this device is using this voltage follower, you eliminate the need for the capacitor. Okay? I cannot stress the importance of this thing. So let's write down the important point here. The key of this circuit lies in the input resistance. There's no application. So advantages. One, by doing this, in so doing, we can drive a low resistance load. And another good thing about this is the low circuit. Another thing about this, it eliminates the need for capacity, for the discrete capacitor. It eliminates the need for a discrete capacitor. So with this circuit, right, you don't really need any gigantic capacitor. And I can tell you, you use this in the input and output. You can even eliminate the need for the input and output. You don't really need so when you buy the chips that can do amplification, they can amplify something like low noise amplifier. You just connect the output, the input and output directly to the circuit. You don't need to care about capacitor. You don't need capacitor. It will work. Why? Because you have this thing so-called voltage follower, common collector amplifier. So I hope this is clear enough for you. So no matter what, I think this thing is important, useful for you. In the coming future, when you are actually become an IC designer, and you will realize that all the bond packs have this device, common collector amplifier. Okay? I don't know whether we have enough time to talk more about another topic. Okay, it's already a 4:15. It's almost time to finish now. And I want to just talk about, oh my God, we have only 13 students. What happened? What happened to the rest of the class? They all run away. Okay. No matter what, right? It's okay, but I can just still continue for a little while. The common collector amplifier, the so-called voltage follower, has this characteristic. And in the next lectures, we will talk about another amplifier, so-called common base amplifier. This is another very, very important amplifier, common base amplifier. And I will explain it to you why. Now, before closing before closing these lectures, I want to tell you, I have sent you a log of lectures slide, and each lecture slide has some homework section at the end of the slide. And if you have time, please do some homework. Today we have finished quite a few things. The common collector amplifier, and common collector amplifier with emitter degeneration. And we have also talked about, a lot of things, yeah. So at least we can do the homework for 3 chapters, yeah. Common collector amplifier with emitter degeneration, and also this one, voltage follower. Common collector amplifier. I will write down the email, and then we will step into. We will try to finish this course as fast as I can. Do you have any questions? Hello?
No question.
Okay, so we are going to stop here. I stopped recording.